Now we will answer the question, how does the number of accessible states change when the external parameter x changes by del dx? So this is the question we would like to answer. How does number of accessible states, which is a function of the total energy E, so this is number of accessible states for energy in the range E to E plus delta E, as a function of x change when x changes by an amount dx. Now, so when we change this external parameter x, there is a certain number of states whose energy is increasing to enter the range E to E plus delta E, and the number of states whose energy levels are shifting beyond this range, they will go above E plus delta E. So we have to know the net number of states that are being created in this range. So we have to basically look at the difference between gamma E plus delta E, that is the number of states which are shifting their energy levels above E plus delta E, minus the number of states that have their energy levels shifted to enter the range E plus delta E. So if you look at the answer to this question, will be basically the derivative of omega with respect to x. So if I multiply it by dx, basically I know the change in the number of accessible states, and this is done for a fixed energy E. I'm only interested in how it changes with x, not with E. So this is for a fixed energy E, and the d omega will be equal to the number of states that are entering this range E to E plus delta E, minus the number of states that are leaving this range. The energy is shifting above E plus delta E. So if you look at this expression, when I divide by delta E and multiply by delta E, and remember delta E is a very small energy, it's so small that the number of accessible states is not changing between E and E to E plus delta E. You can see basically this is the definition of the derivative with a minus sign. So I see that the change in the number of accessible states will be minus the derivative of gamma with respect to energy multiplied by delta E. So this will be the answer. So d omega here is basically the net number of states that enter the range E to E plus delta E, energy range, minus the number of the net number of states that are leaving the range E to E plus delta E to higher energies. So you can see that del omega del x dx for a fixed energy, this is the change in omega, this is minus the derivative with respect to energy of gamma delta E. Now I have to remember what gamma was. So in the previous discussion we found that gamma is density of states multiplied by the average value of the change in energy, dE bar. So this is omega divided by delta E multiplied by x bar dx. So this is capital X bar. So let me remind you a few things here. One is that we have defined x r to be the derivative of del er with respect to x, our external parameter x, so that when you have xr dx, this is going to give you the change in the energy level for state r. And then we have the average value of x, which is basically the average value of so this is done over all states now. So this is going to be del E bar del x, so that you will see that dE bar is x bar dx. So this is basically a reminder of our definition for capital X. It's the change of energy levels with, due to a change in the external parameter x. And this gamma, the number of states that are entering the range e to e plus delta E, is the density of states omega divided by delta E multiplied by the change in the mean energy, as we have shown. Now this is going to be the derivative with respect to energy of the density of states omega divided by delta E. So let's take the delta E outside, multiplied by x bar. So here is my delta E. That is omega divided by delta E is the density of states. And then I have, you can see here another delta E factor. So I have to put this delta E here. And then x bar dx is the change in the mean energy of the system. So you can see that these delta E's will cancel, and then these dx's will cancel, and I will be left with the derivative of omega with respect to the external parameter x is equal to minus the derivative with respect to energy of omega x bar. So if you look at the derivative of omega with respect to x, I can write it as del omega del x is equal to, so I look at the right hand side of the equation, so I'm operating this energy derivative. I will have minus del omega del E multiplied by x bar, and then minus omega del x bar del E. So if I take this equation and multiply it by 1 over omega, you can see that on the left hand side I have the derivative of natural logarithm of omega with respect to x. On the right hand side I have minus the derivative of natural logarithm of omega with respect to energy x bar, capital X bar, and minus derivative of x bar with respect to energy. Now I will argue that this derivative of x bar with respect to energy can be ignored. So how so? So you will remember that the number of accessible states, omega, was basically proportional to the number of values each quantum number can take for f quantum numbers, phi to the power f, and the number of values a quantum number can take is proportional to the contribution to the total energy minus the ground state energy to alpha, where alpha was of the order of 1. And the total energy of the system, E minus E0, is the contribution from each quantum number, epsilon minus epsilon 0, multiplied by the number of degrees of freedom, f. So we find that omega is proportional to at the equilibrium E bar minus E0 to the power f, where f is the number of degrees of freedom, and therefore we have the natural logarithm of omega is proportional to f, natural logarithm of mean energy of the system minus the ground state energy. And this f is of the order 10 to 24, 6.02 10 to 23 of Avogadro's number. On the other hand, if you look at del x bar del E, the second term, we will have this of the order of x bar divided by E minus E0, so the change in the energy. And this is going to be much smaller. Why? Because if you take the derivative, natural logarithm of omega with respect to energy, you will see that this is f times E bar minus E0. So this will be of the order of Avogadro's number, so it's going to be huge, whereas here I have x bar divided by E bar minus E0 at equilibrium. So this is much smaller than the other derivative, which is f over E bar minus E0 times x bar. You can see that because x bars will cancel, E bar minus E0 is cancel, f is much greater than 1. So basically we find that this term is negligible. Del x bar del E is negligible. So for the derivative natural logarithm of omega with respect to the external parameter x is minus, to a good approximation, derivative of natural logarithm of omega with respect to energy multiplied by x bar. Or we can write it as the derivative of natural logarithm of omega with respect to the external parameter x for constant energy is minus beta times x bar. So remember, beta was defined as the derivative of natural logarithm of omega with respect to energy. We can take it one step further. If you multiply this equation with k, derivative of k ln omega with respect to x will be, since beta is 1 over kt, minus x bar over t. So we find that the derivative of entropy change with respect to external parameter change under constant energy is minus x bar divided by t. And once again, remember, x bar is del E del x average value. So this is averaged over all states R. All right. So we call this del ER bar del X. So X bar is called the mean generalized force on the system. So this is acting on the system, conjugate to the external parameter X. So let's give an example. If the external parameter of interest is the volume V, the work done on the system for quasi-static process will be minus P bar dV, as we have shown it for a gas, and this is equal to the mean generalized force X bar dx. So this is X bar times dV. Therefore, we find that the mean generalized force acting on the system is minus P bar, because P bar is the pressure, mean pressure applied by the system. So acting on the system is minus P bar. So that's the mean generalized force conjugate to volume. All right. Now, so we have, according to our derivation, the derivative of natural logarithm of omega with respect to our external parameter V under constant energy is minus beta X bar. So that's equal to beta times P bar, mean pressure. So this is basically P bar divided by Boltzmann constant times absolute temperature, and this implies that the derivative of K ln omega with respect to volume for constant energy is P bar divided by T. So we find that the derivative of entropy with respect to volume for constant energy is P bar divided by T. So you can see that if you know entropy as a function of the volume, we can calculate from the derivative of S with respect to V the mean pressure applied by the system can be calculated. So the information of how omega varies as a function of X and energy is quite valuable for us. Now, if I look at what I have obtained here for the derivative of natural logarithm of omega with respect to the external parameter X under constant energy, this is minus the derivative of natural logarithm of omega with respect to E, that's for constant X, right? This is our beta, multiplied by, so I have to make sure this is lowercase x, and here I have capital X bar. If I take this to the left hand side, so you can see that if I write the change, infinitesimal changes in natural logarithm of omega, which is a function of E and X, this can be written as the derivative of omega with respect to E multiplied by dE plus the derivative of natural logarithm of omega with respect to X multiplied by dx. So the derivative of natural logarithm of omega with respect to X, so from this one under constant energy multiplied by dx is equal to minus the derivative of natural logarithm of omega with respect to e x bar dx, which is dE bar. So x bar dx dE bar is the work done on the system, and this is for an adiabatic process. Adiabatic process, quasi-static process, so that the Q contribution is 0 from the first law of thermodynamics. So I will have the change in the natural logarithm of omega to be del ln omega del E dE. This is the first term, this term, and then the second term minus the derivative of natural logarithm of omega with respect to energy dE. So we're taking this at equilibrium, so this is all for equilibrium. So this is going to give me exactly 0. So basically I find that the change in k ln omega, which is the change in entropy, will be equal to 0 for an adiabatic quasi-static process. And this actually is quite evident if you look at the quasi-static change in entropy is actually d bar q over t, and since you have d bar q is equal to 0, this will be 0 over t for adiabatic process. So indeed the change in entropy is expected to be 0 for an adiabatic quasi-static process. All right, so the quasi-static work changes the energy of an adiabatically isolated system, but the entropy is unaffected. So this is our main conclusion. The effect of changing the external parameter adiabatically is to change the energy of the system according to the first law of thermodynamics, but the entropy is unaffected. So let's summarize what we have found out here. So from our discussion on thermal interaction, we had the following: beta, which is the derivative of natural logarithm of number of accessible states with respect to energy, and this is evaluated at equilibrium, so this is evaluated at E is equal to E bar. So this at E is equal to E bar gives you the thermal equilibrium beta value, which is 1 over Boltzmann constant times temperature. Now if you have a change in the external parameter of the system, then you also have the derivative of omega with respect to your external parameter x for a constant energy. So this I can write as for constant external parameter x, and this is for constant energy. So let me not confuse these two. So this is for constant x, and its value at equilibrium is the value when it's evaluated at E is equal to E bar, and this is for constant energy. The change in the natural logarithm of number of accessible states with respect to a change in the external parameter x is equal to minus beta capital X bar, where X bar is the mean force conjugate to the external parameter X, and X bar is by definition the derivative of the mean change in the energy levels with respect to the external parameter X. And we found that this also implies two things. One, the change in the entropy is zero for an adiabatic quasi-static process. And in general, changing the external parameter of the system has the following effect. So if you multiply this equation by k, del k ln omega del x for constant energy, this gives us minus x bar over t. So the entropy change with respect to the external parameter x for constant energy is given by minus the mean generalized force conjugate to the external parameter x divided by t. So these are our main findings for the number of accessible states. And the number of accessible states is changing with energy and with the external parameters of interest, that is x, and the number of accessible states also varies with energy as E bar minus E0, the ground state energy, to the power f, where f is of the order of Avogadro's number, which is 6.02 10 to 23. So it's a big number. And how did we reach this conclusion about the variation with respect to the external parameter x? Well, we've looked at the number of states entering this region, e to e plus delta e, and leaving this region. And we have shown that the number of states entering this region is density of states multiplied by the change in the energy, dE bar, which is x bar dx. So, and the number of states that are leaving will be the value of gamma evaluated at e plus delta e. And the change in the number of accessible states is minus d gamma dE times delta E. And we have shown that this reduces to del ln omega del x at constant energy is minus beta x bar, by recognizing that the derivative of x bar with respect to E is rather small compared to the derivative of natural logarithm of omega with respect to E multiplied by x bar, and that comes from the fact that the number of accessible states varies with E minus E0 to the power f. And we have shown that in the case of x is equal to v for a gas where the work done on the gas is minus p bar dv for a quasi-static process, this is equal to x bar dx, which is equal to dE bar if it's adiabatic. So d bar q is 0 adiabatic. In that case, it is equal to dE bar. So this, the mean generalized force acting on the system is minus the pressure applied by the system, minus the mean pressure. And we have shown for this case the derivative of entropy with respect to volume would be equal to mean pressure divided by temperature. And the change in the entropy, if you look at the infinitesimal changes in ln omega, so first you have to take a derivative with respect to energy for constant x multiplied by dE, and then take a derivative with respect to x for constant energy multiplied by dx. So this is done for constant x, this is done for constant E. You see that the change in entropy must be 0 for an adiabatic quasi-static process, which is quite evident if you look at the expression for infinitesimal changes in entropy for any process, which is d bar q over t. So d bar q is 0 for the adiabatic process, so it's going to be equal to 0. So that concludes our discussion of the change in the number of accessible states with respect to an external parameter x, and we have summarized the results as we are interested in the change in natural logarithm of number of accessible states with respect to energy. The derivative gives us beta, and the change with respect to the external parameter x derivative gives us minus beta x bar, mean generalized force, where x bar is by definition the mean change in the energy of states with respect to the external parameter x.